Okay, so we're going to talk about base solutions of bases. First, we'll talk about strong bases. The word strong here is used in the same way that we use it with acids and electrolytes. It refers to the extent of dissociation or ionization. So a strong base is one that dissociates completely in solution. The hydroxide ion concentration is equal to the concentration of the base. Most of the strong bases are going to be group 1A or 2A metal hydroxides because those are the more soluble of the hydroxides. The rest of the hydroxides are pretty insoluble. So we use sodium and potassium hydroxide a lot because they're inexpensive and easy to deal with, and they're quite soluble. Strontium, calcium, and barium hydroxide, each of these has 2 hydroxide ions for every formula unit, so that needs to be considered when you do calculations. So I always get ahead of myself. The group 1A metal hydroxides are highly soluble, so we can form concentrated base solutions, and that's helpful. The group 2A metal hydroxides are also used, but they are limited because they're only slightly soluble. So you can't make very strong solutions of them, but they do produce 2 moles of hydroxide per mole of base. These dissociate in one step, unlike diprotic or triprotic acids where the hydrogen ions come off one at a time. This is just an ionic compound. It dissociates completely. All the hydroxide ions are separated. And then we have weak bases, which are like weak acids, and these do not ionize or dissociate completely. The most common weak bases produce hydroxide by accepting a proton from water. So they don't actually have hydroxide in the formula. So we often will use the letter B to just represent a base, generic symbol for a weak base. So a base plus water, bases accept protons. So the base is going to accept a proton from the water, and that leaves the water as a hydroxide ion. So a base is a substance that produces hydrogen ions in solution. A very common weak base is ammonia, NH3. Put that in water, forms an equilibrium where we get ammonium ion and hydroxide ion. We talked about acid ionization constants, Ka. We also can have a base ionization constant, Kb. We use this to quantify the strength of a weak base. So Kb is calculated looking at the weak base reacting with water to form the conjugate acid and hydroxide ions. And so we have Kb is the equilibrium constant for this equilibrium, the BH plus concentration times the hydroxide ion concentration, divided by the concentration of the weak base. Concentration of water doesn't show up in there because it's a liquid and its concentration doesn't change. So a smaller Kb means a weaker base. Small Kb means that the equilibrium lies more towards the reactants. You don't get as much hydroxide produced. And just like we did with Ka, we can also look at pKb. Remember, P is a function, means negative log of the thing. So pKb is the negative log of Kb, just like the acids. So here's a table from your textbook showing some common weak bases. If you look at their formulas over here, they're not going to strike you as a base, right? They're like, how do I know that's a base? You should be able to recognize things like sodium hydroxide or calcium hydroxide, right? Those are bases. Those are strong bases. These are weak bases. Just stretching? Okay. One thing that a lot of these have in common, though, is nitrogen. So we have methylamine, ethylamine, pyridine and aniline, these all have nitrogens. And so we can actually think of these as being substituted ammonia, where you have different things substituted in for the hydrogens. And these will act as bases in the same way. So here's CH3NH2. This is like ammonia, where you have the CH3 group sitting in for one of the hydrogens. This is going to do the same thing that ammonia does. It's going to take a hydrogen ion from the water, and so then you're going to get CH3NH3 plus and hydroxide ion. The KBs at room temperature are listed over here. Those are not things that you memorize. We also have the carbonate ion and the bicarbonate ion, or hydrogen carbonate ion. And as the asterisk says, the carbonate and bicarbonate ions must occur with a positively charged ion, such as sodium, that serves to balance the charge, but doesn't take part in the ionization reaction. You can't have a solution of just anions or of just cations, because nature really hates it when you separate the electrons like that. So if we want carbonate in solution, we need to use a soluble carbonate compound like sodium carbonate or potassium carbonate. So carbonate ion acts as a base by taking a hydrogen ion from the water, which gives us hydrogen carbonate ion and a hydroxide. Hydrogen carbonate ion can also take a hydrogen ion, giving us carbonic acid and hydroxide. Carbonic acid is an acid, right? But in all of these reactions, we have an acid on one side and a base on the other, right? Because when this acts as a base, it becomes the conjugate acid. Yeah, I'm just getting ahead of myself all over the place.
Do we need to memorize that strong base table?
Do you need to memorize the strong base table? I think you should just remember that metal hydroxides are strong bases. Yes?
So, just how strong acids create weak bases, is it like the same thing vice versa? Like a weak base will create a stronger acid?
So we will look at that. A strong acid, its conjugate base is so weak that it just doesn't even act as a base. But we'll get to that.
Okay.
So you're even getting ahead of me, getting ahead of myself. So that's fine. Weak bases, many of these are amines. And so here we've got it all drawn out so it's easier to see. So here's ammonia. The nitrogen has a lone pair, and there's 3 hydrogens here. And so it can take a hydrogen ion from the water molecule. This hydrogen ion, H+, doesn't have any electrons. So here it's sharing a pair of electrons with oxygen. It can leave its pair of electrons over there and come and share this pair with the nitrogen, and we get ammonium ion. This is methylamine, very similar to ammonia, but instead of a hydrogen over here, we have a carbon with 3 hydrogens on it. This is a methyl group. And so the nitrogen acts the same way. It'll take a hydrogen ion from the water, and so here we have the hydrogen ion on here. We get a positive charge on the nitrogen, and we have hydroxide ion forming. So if we go back to this table, all of these guys with nitrogen, those are all amines. And it's the nitrogen that's acting as the weak base. So if you see a compound that has carbons and hydrogens and a nitrogen in there, that's probably going to be a weak base. So finding the hydroxide ion concentrations and pH of basic solutions. When we have strong bases, the contribution of the autoionization of water is negligible. We can just completely ignore it. If we're looking at weak bases, we're going to do a similar process to what we did with weak acids. So we're going to neglect the contribution of the autoionization of water because that only comes into effect with a weak base at a very, very low concentration. We make an ice table, we use the Kb expression to find the hydroxide ion concentration. Here's an example. This is a strong base. Find the hydroxide ion concentration and the pH of a 0.010 molar barium hydroxide solution. So it might be helpful to write the equation for this forming hydroxide ions. So barium hydroxide, this is a strong base. It's going to ionize completely. It's going to give us barium ions and hydroxide ions. How many hydroxide ions am I going to get? 2. I'm going to get 2 hydroxide ions for every 1 mole of the base. So if I have a solution that is 0.010 molar barium hydroxide, whoops. Actually, let me write this out. Moles of barium hydroxide per liter. I want to know how many moles of hydroxide per liter. Got 2 moles of hydroxide for every 1 mole of barium hydroxide. So the hydroxide ion concentration is 0.02. Now, you don't have to write all of this out, but I've written it out here because I want you to see what the process is. When I look at BaOH2, I see, 2 hydroxides. So whatever the concentration of the base is, for the hydroxide ion concentration, it's going to be twice that much. Okay? So that is hydroxide ion concentration. How do we find the pH? pH is the negative log of what? H plus concentration, or H3O plus. Well, I don't have that. Remember the circle of pH? I could calculate POH, it's the negative log of the hydroxide ion concentration, because I have the hydroxide ion concentration. And then remembering that pH plus POH equals 14, I can convert that to pH. So POH is the negative log of 0.020. That's not my calculator. So that's going to be 1.69897. pH equals 14 minus that. So 12.30. Any questions?
So it's super basic.
Yeah. Yeah, this is super basic, and it's a super basic calculation. Now, you can have a solution that's much more basic than this, right? Because 0.02 molar hydroxide that's actually a very low concentration. Because what if we had like 5 molar sodium hydroxide? That'd be a lot more, right? So 0.02 molar and 12.3. Let's do a weak base. Find the hydroxide ion concentration of pH of a 0.33 molar methylamine solution. So when we see amine in here, we don't need to worry about what's in front of it. That's just a weak base. And we look up the Kb. I already did that. This is our Kb. So it's helpful to write out the reaction. What if I don't know the formula for methylamine? I'm just going to call it B for base. And isn't it convenient that there's no element B, and there's no element A, and there's no element X? There is a B. My apologies, boron. He's just, whew, okay. Yeah. I should have known that was a tangent. I shouldn't go on. Anyway.
Were you thinking beryllium?
I was thinking of beryllium, yes, and barium and all the other guys, and I forgot about boron. He's kind of boring right there. He's a bit of a moron, too. Anyway, B, not boron, B for base, plus water will be in equilibrium with Hb plus and hydroxide ion. If that GC auto sampler noise bothers you, feel free to close that door back there. So we need an ice table. So this is our base. Its initial concentration is 0.33 molar. We don't need to worry about water because its concentration doesn't change. What's our initial concentration of the conjugate acid? 0. And how about the hydroxide ion? 0. I'm a detail person, so I put approximately. It's so small, we call it 0. And then we'll put some x's in. So this is going to decrease by x, that will increase by x, and this will increase by x. And at equilibrium, we have 0.33 minus x, and we have x and x. Our Kb expression, Kb is equal to the conjugate acid times the hydroxide divided by the concentration of the weak base. So we can plug things in here. We have 4.4 times 10 to the minus 4th is going to be equal to x times x, x squared, over 0.33 minus x. So we can use the solver, or we can try the x is small approximation. I just did x is small and came up with x is equal to 0.0120. And dividing that by 0.33, I get 3.7%, so it's okay. I'm looking for hydroxide ion concentration. That's going to be equal to x. So the hydroxide ion concentration is equal to x, which is 0.0120 molar. It's probably just 2 sig figs. And then the pH. Whether it's an acid solution or a base solution, we almost always talk about pH rather than pOH. So we're going to do a lot of this hydroxide ion concentration to pH. So what I'm doing is I'm finding the pOH. It's a negative log of 0.012. And then pH is 14 minus that. .08 is our pH. Did I get it right? Yes. Any questions?
If it's equal to X, why did we subtract it from 14? Because pH would also be the concentration of the acid, no?
Well, this is not hydrogen ion.
Oh, okay.
This is the conjugate acid,
Okay,
but it's not hydrogen ion.
okay.
Yeah. Any other questions?
For
Mhm.
the X is small approach, you're just basing that off of the equilibrium constant small?
Yeah, the equilibrium constant is relatively small, and this concentration is relatively large.
Okay.
And I just kind of eyeballed this, and I saw that if I could get rid of X here, I could actually solve that real quickly.
Yeah.
If it wasn't much simpler with X is small, I wouldn't even bother. I would just use the solver on my calculator. Yeah.
To check if X is small, we can divide it by an initial.
So to check with X is small, I take what my X ends up being, and I look in this equilibrium expression, what am I subtracting X from? I need this to be less than 5% or less than what I'm subtracting it from. Because if it's more than that, it introduces too much error.
Just as the reactants, though, right?
Well, just whatever you're subtracting it from.
Because that could be on products too.
Yeah.
It'd be like 3 different ones.
Yeah, you could have 3 terms that have X being subtracted.
Should check them all.
So then I would check the one that is being subtracted from the smallest thing, because that's going to give me the largest percent and is most likely to have it fail. Yeah. Any other questions?
So only if it's being subtracted? What if it's being added?
Well, added is the same. Added or subtracted. But we never get rid of X when it's like being multiplied, right? It's just when it's being added. Added or subtracted. Because like, tossing an orange onto a big semi-load of oranges, it doesn't matter. Adding 1, subtracting 2, doesn't matter. Yes?
Can you explain again what the amine means?
Want to know what the amine means? So amines are ammonia. There's a similarity between those. Amine, ammonia. An amine is ammonia that has 1 or more of the hydrogens replaced with something else. And they're actually organic compounds, and it's a really common thing in organic chemistry where we have this part of the molecule that we're looking at, and then the rest of it is like mix and match pieces. And it's going to behave in the same way regardless of whether we have an ethyl group there or a propyl group or whatever.
And so we don't have to worry about.
We don't need to worry about what those are. All we need to do is understand that this is acting as a weak base. So anytime you see something with amine in its name, it's a weak base. And that's not something I'll try to trick you with on an exam. I won't try to trick you. Sometimes I do by accident, but I don't try.